Hello, everyone, on Zoom and in person. Um, Welcome to our seminar today. This is the graduate student community at OU weekly seminar series. Today we have Dr. Liu and Dr. Fisher, both from Oklahoma State University. And I am very excited to introduce both of them in just a few minutes. But first, some housekeeping and some introductions for the graduate student community here. First, I'd like to do a brief intro of our leadership team this year. So we both introduced ourselves briefly, but myself and Samuel Espinoza are the co-chairs. Then we have our publicity team, Swapnil and Avinash. I'm sure you've gotten emails from all of them. Make sure you pay attention to those for all our upcoming events and anything else. We have our treasurers, Sivash and Anshu. We have a really helpful, really big support team. Zareen, Lewis, Roshan, Rachel, Naran, Sadikar, Saramya, Viva, and Hafiz. And then, of course, last but not least, our faculty advisor, Professor Farokh Mistry. So that's just, if you need any help in your time here as a graduate student, feel free to reach out to any one of us. If you want to join the GSC, we'd be happy to invite you. Reach out to any one of us, and I'll have some contact info for us on another slide coming up. This slide, actually. So we have regular team meetings once per week. This semester, they're Thursdays at 4:30 p.m. We update it every semester so we can get a time with as best availability for the whole team as possible. We hold these hybrid, either on Zoom or in the BERT team room in the engineering lab building. So we welcome everyone. If you'd like to join, please send me an email right here. Oops. Please send me an email or send Samuel an email or both of us, and we'll be happy to get you all the information. And like I said, we update these every semester. So if it conflicts this semester, we'll be able to make a change so that you'll be able to join in the future. This one's really important so that we can keep hosting these seminars and all of our other events like the food festival, meet and greet. If you're not a member of the GSC on Engage, please either search for the GSC on Engage or scan this QR code right now. All it takes is your OU login and then just click join. It helps us keep getting funding from the SGA and, like I said, hosting these events. Right. And then we also have a LinkedIn page. Of course, you can search for us on LinkedIn. You can scan the QR code here right now. It helps a lot with networking, both with current events and former members that are already in academia, already in industry. You might be able to make some connections. So please join if you're interested. And then one more is our Facebook and Instagram. Pretty similar. We post all of our events on here and some other updates, just in case you're not on LinkedIn or something like that. But there's a QR code for each. And of course, you can just search for us too. Yeah. Leave that up for just a second in case you're scanning. And 3, 2, 1, next. I think this is our last of our social medias, but I really like this one. We also have our YouTube page where we host almost all of these seminar videos over the last 4 years or so. But you can scan this QR code, you can search for it on YouTube. But if you ever missed anything or you saw part of a talk, had to leave, or just wanted more information, you might be able to get the speaker's contact information from this video, or you can always reach out to us at the GSC. All right. And next up is the Dave and Sue's BERT team room. I mentioned it a little bit about our meetings. This is in the engineering lab building. 4 graduate students for GSC members. It has card swipe access. So if you need a place on campus to, rest on a couch, use a microwave, use a coffee pot, have a meeting, we have chairs, couches, coffee pot, microwave. But email myself or Samuel or Professor Mystery and join the GSC, and we can make sure you have access to that. All right. Next up, we have a attendance sheet that Samuel's going to add to the chat on Zoom. We'll also have one in person. But please fill this out. It helps us, know who's attending, but also justifies it for the SGA and to the university so that we are allowed to keep doing this. All right. So there's a lot of words on this slide. I'm just going to hit the main points. Most of you have already attended at least one of our seminars this semester. Our theme is exploring research frontiers with generative AI, issues, methods, and applications. So we're bringing together speakers from all over the country, all over the world to share their experiences, what they're working on, what they're having troubles with. So especially on how can people work with generative AI to create intellectual, economic, social value, and connect different research domains. And then the more technical, actual research issues, methods, applications, things like that. And then looking at the benefits, whether it's economic, social, energy savings, whatever that may be. So if you're interested in this, like I said, we have YouTube. We have videos up on YouTube already, and we have plenty more speakers this semester if you can attend. All right. And then I'm almost done. I promise we'll get to the interesting speakers. But we have some upcoming events. The biggest one is next week on Thursday, October 23rd. We have our ASME lightning talks hosted with the Central Oklahoma chapter of ASME. So this is where 3 students will present their research in 10 to 12 minutes in a lightning style format, and then have discussion with the audience, discussion with professors, industry members, whoever attends. There's usually quite a few industry members that attend these. This year, there's an event on campus that'll take up a lot of parking. So we decided to do it hybrid. You'll be getting a Zoom link if you haven't received it already from Bethany or from us directly at the GSC. And then the week after, we have Dr. Husky is presenting on ethical AI from a really different perspective. She is from the Department of Classics and Letters here at OU. So we have one that's not so technical, but we still get some super valuable information from it. And then after that is Dr. Gamarian from AME here at OU, and demystifying generative AI in 45 minutes. With that, we can get on to the interesting speakers. Today is exciting. We actually have 2 speakers, both from Oklahoma State University. First, we have Dr. Liu, who completed his PhD at Purdue, and has been working especially on compressors on the refrigeration cycle, has actually implemented AI in load management, right? Paper? Yes. Sorry, just making sure I'm not putting words in people's mouths. And then we also have Dr. Fisher. So if you've used Energy Plus, you've used his work. If you've taken Dr. Song's course here at OU, AC Systems, you've seen his work in the books, in the textbook. So we're really excited to welcome both of the speakers today, Dr. Liu and Dr. Fisher. And I'll leave the stage up to you 2.
Okay, very good.
And I'm going to pop up your slides real quick.
Okay. Great. Okay, very good. Will AI make or break an engineering career? That's the question. Here's a much more representative picture of me. The other one is like 30 years old, but still up there on the OSU website. So we are very, very happy to be here today. As Rodney said, I'm a longtime Energy Plus developer, worked for many years in building heat transfer and system simulation, and am now, I was the founding director of the Zinc Center, but now very recently, I'm the director of the Center for Integrated Building Systems, which is a research center at Oklahoma State University. Very, very complementary work to what Dr. Song and her students are doing here in AME. So we're very glad to be here. I'm going to just introduce in a few slides the Center for Integrated Building Systems at Oklahoma State University, and then Dr. Liu is going to come and really do the heavy lifting here on the talk. So ZIBS, as we call it, is really 6 core faculty collaborating with HVAC&R industry partners, and we work with these industry partners to develop research proposals, to oversee the research, guide our graduate students and undergraduate students, and then we also have quite a bit over the years. We've built up and continue to build the research infrastructure there. We have about 30 to 40 graduate and undergraduate students, MS and PhD students in mechanical engineering, undergraduate interns in mechanical engineering, and then capstone design teams that our faculty run. So just a quick overview and a peek at our research laboratories there. We're very much focused on the heat pump side of the problem and the air conditioner side of the problem. So we're looking very strongly at vapor compression cycles, which is what makes it very synergistic with what's going on here at AME. We have an experimental ground source heat pump field where we can do quite a bit of testing. We have a lot of boreholes in the ground up there. And if you ever wanted to come up and do some experiments on them, we would welcome that. That would be great. So we've got some ground and surface water heat exchangers, above ground and below ground thermal storage. And then we have a solar PV, a very small kind of a new setup that's solar PV and ground source integration with all DC components in it, which is pretty interesting. Compressor load stands, and we have access to anechoic and reverb chambers. Here's just a little video of our kind of the core facilities there. You'll see it's very equipment based. This is a compressor load stand right here. You take compressors, you put them on there. That green cylinder at the start of this was a compressor. And then you see here are there's like 3 pumped loops in here, psychrometric rooms, which are big environmental chambers in the background here. Here's a peek into the psychrometric rooms. They're just big environmental chambers where you can very precisely control humidity, temperature, and airflow rates, and you basically have 2 rooms, an indoor room and an outdoor room, and you split the equipment apart, and whatever's outside goes in the outside room, and whatever's inside goes in the inside room. And then we have one more big facility there, which is a coil, a heat exchanger test facility. This is like a big wind tunnel that you can put giant heat exchangers in, actually, like 7-foot by 7-foot heat exchangers will go into this wind tunnel. Unfortunately, I don't have a video of the ground source facility, which you would be most interested in, I think. But we'll get that. We'll rectify that in the future. So the question is, why are we interested in AI? We are not AI experts, but we believe that that's where we have to go. And the reason why is that sustainable and integrated building systems really are a target-rich environment for AI. There is loads of real-time data available in modern buildings, not on the residential side yet, but in commercial buildings, there's a lot of data out there, and we believe that with Dr. Song's work getting out there, this is going to be true on the residential side as well. That buildings will be instrumented, that there will be lots of data available both for commercial and for residential buildings. And of course, buildings are a really, really important part of the puzzle for reducing energy use and the carbon footprint. They're a big, big piece of this pie, about a third, I believe. And so while we have opportunities to engage here, there's a lot of hardware that's out there. We saw a whole bunch of it in the smart house. It's really neat. It's necessary to integrate the AI machine learning models with our physics-based models in sort of a hybrid combination in order to really optimize these the built environment. Okay, smart is not going to be good enough. It's got to be smart and always learning. That's how it will have to be. So we need these learning algorithms embedded in the building control architecture. We need that to happen, and that's why we're really excited about collaborations with all the research that's going on in data science, in developing machine learning algorithms and AI algorithms. All right. With that, we go to AI 101. Dr. Liu, come on up and introduce yourself.
Thank you, Dr. Fisher. It's a great pleasure to be here to talk with everyone about AI. And I'm a new assistant professor, just joined the Oklahoma City University. This is my...
Rodney gave you a promotion.
Yeah.
Did you notice that?
This is 8 weeks. Yeah. So not an associate professor. I'm still working on that. Probably take a few years to do that. So as Dr. Fisher just already discussed, right, we are interested in using AI, but we are not really researchers on AI. So that's why I think I will first cover just a little bit of fundamentals of AI from what I just learned last 2-3 years of playing around with different algorithms. And then I will give you one example where we used machine learning in our compressor-related research, and then showcase why we need to be careful with AI because there are potential issues. And then lastly, I will give the stage back to Dr. Fisher talking about engineering leadership, as he's a real leader compared to me in this stage right now. So what is really AI? I guess we talk about artificial intelligence every day. One definition, an easy one, is really machine perform tasks that need human intelligence. And with the right data and right model, AI can be very powerful and useful to solve many problems. But it's actually, the challenge is to find and create the right data and training sets for the model, right? That's a lot of research that happening in the building fields right now, like Dr. Song's work is to trying to get more data in residential world so that we can, well, what do we do with the data is the next step, but the first question is really how do we get the data and make sure the data are in good quality. So here's a kind of overview of all the different algorithms that are popular in the AI world. And you sometimes will see people interchangeably using artificial intelligence with machine learning, but they are not really the same thing, right? So machine learning is kind of a subset of AI using machine as a platform to learn things. And the other popular AI-related term is large language models, which is really like ChatGPT, Gemini. So all these are, again, a subset of machine learning. And then within this, we are having several, I guess, coverage with deep learning, which is part of the machine learning. And then the large language model is really part of the deep learning, and its intersection with the natural language processing and the conversational AI. So we are engineers, so that's just be careful when we use different terminologies when we describe our work. I have been in multiple presentations where like one term is used, but really, the speaker wants to refer to a different term. And just for a disclaimer, I guess there are different ways how you categorize this into different cycles. But this is just one way of doing this. So what are the different types of AI? In a pretty well acknowledged way, we divide the AI into general AI, GAI, and narrow AI. So I'm putting two examples here. And by the way, both of these figures were created by AI. I just told them, hey, I need a fancy looking robot. And they gave me this nice picture. So the general AI is like a real robot, looks like a human. It can do generic stuff. It's not limited to one function. And then a narrow AI really have a very specific function. For example, you can develop an algorithm that help you drive your car, right? That AI only knows how to drive. If you ask him to solve your engineering homework, he will be very confused. But general AI can give you some guidance on homework, but if you ask the general AI to drive you from one place to the other place, they might be struggling as well. So here are a few more examples to what we use daily on narrow AI and general AI. So facial recognition, chess playing, some of the virtual assistant. Also this algorithm used by like TikTok, Netflix to find the right videos for you are the narrow AI. And then more general AI is like chatbot, ChatGPT, and some of the characters we all love in Star Wars are all general AI, and the other one is Terminator. Right? It's kind of a general AI, although it's more specialized in killing people, but it can do a lot of other things, like driving a motorcycle. And then let's dive a little bit deeper into this machine learning. This is an important part of this AI trends that we are facing. And really from the name, it's learn from the data to make predictions or decisions without explicit in programming. So without explicit in programming is kind of the difference between machine learning versus like a dedicated algorithm to solve problems. So typically we have three functions for machine learning. Classification, like shown here. Let me have my laser pointer. Showing here, you can classify things into different categories. Also, you can tell a picture from it's a dog or it's a cat or it's some different animal. And then you can also do clustering and then regression. Clustering is like set different data sets into different categories. And regression is really finding the trend of a given data set. So it really works from three steps. You have some data, you need to process the data, you feed the data, and then there will be an algorithm where they can be trained, and the trained algorithm will be make predictions or decisions. So just use one example here, dogs versus cats. So you have different ways of training your machine learning model. The first one is kind of called supervised learning. So the machine has a supervisor, which is a human. And the first thing you do is label the data. So one example here, if I have all these pictures I found as dogs, I can label them as dog. And then I can find another 1,000 pictures of cats, and the categories label them as cat. And then I can give the algorithm saying, no, you have all the pictures of dogs and cats. Please learn learn is really the magic part where I don't really get that deep into that part, but then they will find the characteristics, the features. And then last step is if it works, when you feed him the AI a picture of a dog or a cat, they will try to identify these features and tell you whether it's a cat or dog. And then the second one is really unsupervised learning. So you still feed the same pictures to the algorithm, but you don't tell the algorithm what's a dog and what's a cat. You ask the algorithm to try to identify by themselves. There are common features. This works in some case if you have a distinguished data you can look at, but if you just feed things where really AI doesn't know before, they may be very struggling on figuring out what you want. And they may come with very different criteria on, for example, like if you feed this to data sets, they may say, oh, I have some animals or some figures look like a brownish and some look like black and whitish. And then they will basically use this as the categories instead of using dog and cats. So the third one is reinforcement learning. So it basically, it's like how humans learn. That's also what ChatGPT is sort of based. You don't really give a category, you just tell AI to make a prediction, and then you give a feedback to whether this is correct or not. Or in the AI terminology, they give a penalty or reward. So if the AI is saying, oh, this one is a dog, just by guessing, and then you tell the AI, you did a good job, keep going. And if it says it's a dog and you say it's wrong, you say, oh, sorry, you really made a wrong guess. And over all the data, they will try to say, oh, based on this criteria, I'm leaning towards more rewarding, and based on different criteria, I'm leaning towards more penalty, so that they can, learn in the process. So many of the game playing AI, like AlphaGo for, and also maybe for chess and other AI are trained using this reinforcement learning, because you can really just play with the AI until you lose and you win, and ultimately they will find the ways to win. So that's the reinforcement learning. And then dive even deeper into the machine learning. I kind of picked the topic where I use the most, right? So that I can kind of give a seminar without saying wrong things. So the artificial neural network is something at least I use a lot. And when I started with trying using AI in engineering research. So it's a computational model that kind of simulates or emulates human brain structure and function to do pattern recognition and predict the result. And the setup looks like this. You have multiple layers, and within each layer you have different nodes. And then within the layers and nodes, you have bias and activation functions, where it's basically kind of a weighted passing road, and you can have multiple hidden layers in between, but in the end you have your inputs and your outputs. And the idea is if you feed enough data, they will learn what happens inside this process and get to the correct output. You have different structures: feed forward, feedback, convolutional, recurrent. It takes probably a week to explain the details here, so I will just kind of skip the details. Lastly, I have to talk about large language model for the completeness, as everyone is now probably using generative AI. It's the keyword here is a language model. It's trained with self-supervised machine learning on a vast amount of tasks designed for natural language processing tasks, especially for language generation. And The largest and most capable one is called the generative pre-trained transformer. And you have billions of trillions of parameters. And it's evolved from this revolutionary neural networks. It's very powerful, right? But the key here I want to emphasize, this is a language generating model. So maybe the latest version have some reasoning embedded, but for example, ChatGPT 3 and 4, they are really just trying to predict what is the most relevant word based on your question. They don't really understand what you are asking. If you put heat transfer in it, the AI supposedly has no idea what is heat transfer, but then they will just search. If you talk about heat transfer in buildings, what is the most relevant word that will come out from literatures, from internet search? And then they may see energy plus usually comes with heat transfer in buildings. That's then they will kind of spit out the next word. Maybe we need to use energy plus for heat transfer in buildings. Of course, it's more complicated than that, but they have really no domain expertise on the question you're asking. It's just trying to find the trend, which is the most popular word that associated with heat transfer and buildings. So that gets to kind of the challenging part of using AI is you need to be the judge of whether they are giving you something reasonable or it's just a guess that really feels like writing nice grammar, but maybe makes no sense. I put a picture here. This is the September 2025 Nature cover. And then the paper, they highlighted this really reinforced learning to teach AI model to improve itself. So this is where it is going. So trying to have more logic built into this large language model. And I believe this is talking about the kind of the DeepSeek, another different chatbot that supposedly use only like like much less energy to train and to get to the same performance as ChatGPT. So now let's go back to AI to engineering, and I'll give you an example finally where we use the AI and reached pretty good results. You can do this for a lot of things. I highlighted reduce order modeling, so that's what I'm going to show you where we used AI in one case. But connect with the building research, like predictive maintenance, intelligent automation, real-time data analysis. Those are all very promising directions where AI can be used for engineering. And generative AI can help you with the design, right, to generate new structures, mixtures. There are people using AI trying to find the best refrigerants for the future, and basically just mixing all the possible refrigerants and ask AI to predict the performance and put in a system and see which one works the best. But again, keep in mind, they don't really know what is a refrigerant. They just trying to follow the previous training data you feed and do the same thing for the future tests you are giving to the AI. So here's just one simple example. We used this ANN for a reduced order modeling for vapor injected compressor. So let me just explain a little bit of the background. We have a vapor compression cycle here from a pretty standard, I guess, thermal 1 class. And you have a refrigerant goes into the compressor, superheated vapor, and get compressed into a higher pressure and goes through the condenser where you can reject the heat, and then goes through an expansion valve, goes to low pressure, low temperature, goes through an evaporator where you can take or absorb heat from the environment. And depends on where you put your condenser and evaporator, this can be a heat pump or this can be air conditioner. And on the right, I'm showing the pH diagram. Let me hide this. where you have the pressure changed with enthalpy. And you go from, again, 1, 2, 3, 4. So this is really 2 to 3 is where you reject heat, and 4 to 1 is you absorb heat. And this can be your indoor and outdoor site. But one problem we are facing with this cycle is when you have a very low ambient temperature in very cold operation, you may have a high pressure ratio to lift it up from 0.1 to 0.2. And what will result in is a very high loss in the compression process, as well as a super high discharge pressure because of the friction, and the friction will convert into heat, and heat will be brought by the refrigerants to the discharge. And ideally, you do not want to have too high of a discharge. There are issues with reliability, oil degradation. So one idea people are playing with is let's put some of the cold fluid from the cycle and inject it into the compressor midway of the compression, so that you can reduce the superheat and save off some of the compressor work in the process. Please note, I really put a simplified version of the cycle here. The real cycle will be more complicated. That's why I put a kind of a dash or a fake exchanger just to show we will use this to control the injection state. So one obvious benefits you can get here is you have a reduced discharge temperature. Originally at 0.2, now you can go to 2 prime. And you can also save some compressor work. The area in the pH diagram is indicated in this green dash line. And you can also do advanced circle design where you can also do additional cooling or heating with the steam you've taken out from the process. So here comes the question, or the problem statement is, if we have this new compressor, how do we model this, and how do we integrate the compressor model into a system so that we can identify what is the best operating condition, best design for this injected compressor? So we have a mechanics-based model. I will skip that part. It took a few years to develop that model. Consider all the physics happens in the compressor. However, as you know, mechanics-based model, especially with fluids, it takes a long time to solve it, right? And then if we think about this cycle model, we want to have, of course, knowing how the system performs on top of how the compressor performs. I'll just give you some numbers here. The mechanics model we developed takes probably a few minutes to solve one compressor operating condition. But for the system level model to converge, you need sometimes 20 to 30,000 iterations per condition for a high fidelity model, which means only the compressor model itself will take 40,000 minutes to solve one condition. And if you want to use this system model into the building model, you need a few thousands of iterations for the system level model to be embedded in the building model, because you need to consider different weather, different location. So soon enough, you end up with, if you want to solve the new compressor design in a building model, it takes you a few years on a laptop. Or if you have a supercomputer, it still takes a lot of time and energy to solve that. So what we really want to do is just use ANN as a tool to help us make our compressor model fast, right? We want to go from 2 to 3 minutes to just a fraction of a second. And it's really kind of exploratory study a few years ago. And we decided, okay, this is a tool that everyone's talking, let's give it a try. So what we did is we use, like I said earlier, the tricky part of this AI business or machine learning business is how to get data, right? So what we did was we used our mechanics-based model to generate good data so that we don't need to build a test stand and spend a lot of time to do the experimental testing. So first we have our defined operating envelope, and we have the mechanics model developed. We will use experimental validation for selected operating conditions so that we know this mechanics-based model is accurate. And then we will use the mechanics model to generate thousands of data where you cannot do it in experiments. And then we feed this thousands of data points on compressor performance to the A&M model. We use a 70-30 split for training and testing. And we just check whether the A&M model can accurately reflect or predict the mechanics model behavior. And once we got the incomplete or not converged, not good enough data, we just go back and increase the A&M model complexity. And once we got the good data, we will use this AN instead of the mechanics-based model to be our compressor map that we will put into the system level model. So this is kind of the results we ended. We take a 5 input. This is really the compressor operating condition, the condensing temperature, the evaporating temperature, the injection temperature, injection timing, and the compressor speed. And then there are 2 hidden layers, each have a few nodes. And you got to the compressor performance, where is the mass flow rate, the work output, and then the discharge temperature and the efficiency. And those 5 input will be then coupled to the system level model. And if you want to do this for the system level model, you can continue on this road, right? You can have layers of reduced order model from your component to your system and eventually to your building. Just to kind of show the results here, we checked the predicted results versus the mechanics model results. And as you can see, for the 3 key parameters, compressor mass flow rate, injection mass flow rate, and power consumption, we got pretty good accuracy within 5% for most. So again, this is pure machine learning based using the data we achieved. What we are trying to do right now or moving forward is, like Dr. Fisher said, we want to have this mechanics-based model built into the ANN so that we have some physics. Instead of just having these random layers, maybe we'll guide the machine learning model, like saying, how do you couple these parameters together and what do they play in determining the performance? But that requires really more deeper dive into the machine learning algorithm itself. So this concludes kind of the good part of AI, but AI can also be wrong or being tricked. So the first biggest issue is the data bias. So AI only learn from the data they are given, right? So if you provide the improper data or biased data, you will get biased performance. One example in the building world is if you have data from US is on 50 hertz, and if you have things from European, they may on 60 hertz, you will get some different behaviors because of the voltage. You may not even think about it. But if you use all the data in the US, feed it to a machine learning model, and then you try to use it to predict some other parts of the world have different voltage, it will not perform very well. So you need to be really thinking, how do I select my data set so that I have a comprehensive and unbiased data set to train my model? And after getting the model, where can I apply the model? Do I have the same conditions, or if some critical things change, you may need to double check whether your model still works. And AI may also create fake information that may sound very confidently correct. So one popular one is you have cite this non-existing standard or publications. For my personal experience, I got a review for one of the paper I submitted back from a well-respected journal. And the reviewer suggesting I need to add a few reference to the topic. And I Googled the reference, they don't exist. Like they has a paper title, author name, they even have a DOI, but if you copy the DOI into the browser, you got nothing. And then I complained to the editor, and they also checked the same reference, and they were like, yeah, those are not existing. So it's become a problem in academic, and so when you ask AI to do something, please double check the source. And you can also trick the AI, and then they may have either by tricky question, or you can fool the AI on purpose. I have one example here, two examples. This is really on a high level, like what could go wrong with a machine learning model. You have underfitting. This is a good fitting. You can also overfitting, right? So for classification, you probably just want to have this as your classification, but AI may try to really trace what happens and put the two data sets separately. The other, this is a very recent publication, not in the HVAC field, but they were looking at the journal paper published and how many of the citations were counterfeit. And the first article have 20 citations and 18 of them were fake. And this is published, already passing the reviewer process, passing the editor check, published as a journal paper. And as you can see here, some of the ratios are pretty high. I mean, some of them are low, but it really should be 0 on this row, right? If you publish your paper, you put a reference in, you better have read the reference and it's existing, right? So there are issues that are already happening in the academic field for the abuse of using AI. And this is another very interesting example I found. It's a slightly older paper from 2018 in IEEE. But the research group here are trying to trick the self-driving algorithm on a stop sign. So again, AI doesn't really know what is a stop sign, and they use the training data. AI will pick, the features of a stop sign, and then similarly, AI doesn't know what's a speed limit. They will just look at the picture and trying to take the key features of a speed limit. So what this group did is to put this white and black rectangular on a stop sign. In human eyes, this is a stop sign. It has nothing to do with the speed limit. But because the way how they trained the machine learning model, when the machine learning model look at this particular stop sign, because this white and black features are the key features in the training, they actually will take a 45 speed limit if you feed this picture. And they did the testing in, in the computer environments, like a virtual environment. They did the same testing in a real car, and the algorithm will get 45 speed limit at the stop sign. Of course, this has been fixed, right? This is 6-7 years ago, but this shows you when you think the AI is learning, they may not be learning the same way you are thinking it's learning. So you need to be careful. Don't put too much trust in AI and check all the possible scenario carefully. If a car see a stop sign at 45 speed limit, something really bad could happen. And then this is a last slide I have before I hand it back to Dr. Fisher. AI is kind of have good and bad parts, like two sides of a coin. There are a lot of things AI will be doing very successfully, like we talked the pattern recognition, data-driven optimization, modeling, automation, natural language tasks, mastering some closed rule system. But it will feel on this reasoning, logic requires expertise, and some of the safety critical system, you probably don't want AI to do it for you. And then the other big issue is really this accountability and liability. If AI did something wrong, who should we blame in that case? And another interesting data here is from MIT also this year. They look at the over 50 organizations and 300 big initiatives where those organizations are trying to push using AI. For example, like you can have a project where you want to use AI to organize all the seminar instead of our lovely chairs here. And then the successful rate is really low. Only 5% of the AI projects was successful. 95% of the AI project just, unsuccessful and waste a lot of energy and money. So I'll give the stage back to Dr. Fisher to close this up. Some of the, among the leadership side of engineering career.
Thank you very much, Dr. Liu. So AI really is this emerging field is really a make or break issue for engineers. It's kind of like the transition, I think, from the slide rule to the handheld calculator. The opportunities are tremendous, right? So it really does augment an engineer's capabilities. There are lots of ways that you can use it very productively to enhance your productivity. And for sure, there will be new AI-related roles that come along. The data scientists are already here. The prompt engineers for AI, engineers that know how to prompt the AI to get the right results, and the ethics and safety engineer. It's got to really watch the AI to make sure it's not out of bounds. So the risks are really an over-reliance on the AI. And this is the GPS effect, where you just follow the GPS because it told you to go that way, and you end up on some dead-end gravel road out in the middle of nowhere. And you're like, well, that wasn't such a good idea. And then I think the most serious risk of over-reliance is the loss of fundamentals and the degradation of critical thinking. If engineers, especially at the master's and PhD levels, are paid to think, critical thinking is what we need. Accountability and ethics liabilities are really, really. This is something that society at large is grappling with right now. And then there will traditional job opportunities could disappear here. So these come along. A couple of things here: engineer versus AIs. AIs have to follow the rules. Engineers don't. Engineers can break the rules to break the records. Okay, so AI's got to follow the data. They can only work at least reliably inside the box. Okay, they've got their data set. That's where they work. And they can manipulate and curate these large sets of data, but the data has to be there, and it has to be high fidelity data. They can use only statistical methods to build on assumptions, and they can find the signal in the data. But if you go outside the data, right, you're in trouble with a purely regression model. That's why I think in the end you'll have hybrid type models with some physics, hybrid physics-based models, like parameter estimation type models. You can actually extrapolate beyond the data sets, but otherwise you're on very, very thin ice. So creativity and critical thinking is really where the engineers shine and where things need to go. The engineers synthesize the information outside the data to find new causal relationships. Okay, so engineers have got to lead. They've got to be in charge of the AIs. But you have to embrace them, I think. I think if you just say, well, no, I'm not going to do that, I think that's a mistake. I think that they bring so much to the table that you have to embrace them. So what should the engineers do? Solidify your engineering fundamentals. You got to know the fundamentals. Dr. Song said this earlier. The first law is 300 years old, right? And you can't just ignore it. You've got to know that. And then become AI bilingual. This is really important, to become AI bilingual, to understand the basics, to learn to use the tools, to develop the prompt engineering skills to get this done, to use it for pattern recognition. And then the third thing here I really like is to cultivate the uniquely human skills, systems thinking, creativity and innovation, ethical judgment, communication and collaboration. AIs don't do this well. And business acumen, of course. Okay, here's our references. And Dr. Liu put these references together. And you can look at them all here. And there's a couple of AI-generated references in the list. Yes, they made the references. This is a warning to all you graduate students out there who are publishing papers and you're using AI to maybe find references. Oh boy, be very, very, very careful. You can't hardly find them in here. I'm not even sure I can find them. Where are they, Dr. Liu? Do you know?
Are all fake, which is really today's topic.
Yeah, which is quite amazing that you could and they look really, really convincing. Yeah, they're fake. Yeah. Yeah, they look so real. That's the problem. That is the problem. Okay, so thank you very much. We appreciate it. All right. And yes, we can take, we're late already, aren't we? So, but we could take a few questions.
Oh, you'll see. We have the room booked until 1:30. Usually. Yeah. All right. For everyone on Zoom, and everyone in person, a big thank you to Dr. Fisher and Dr. Liu for coming all the way down from Stillwater today, presenting in person. And we are opening the floor to questions. If you're on Zoom, feel free to unmute and ask the question. I'll relay it to Dr. Liu and Dr. Fisher. You can also put it in the chat if you prefer. If you're in person, you can come up here so that the people on Zoom can also hear the question. And I'll stop talking so people can unmute. Is there any in the chat? There's people. A lot of times people are scared to be the first one, so I'll open the. Okay, yeah, you go.
So it's very informative talk. I learned a lot from both of your slides. I mean, about the definition of AI, machine learning. So I have one technical question to Dr. Liu is, when you do that injection, the compression cycle simulation, right? You related in the neural network model. So how did you define the 2 layers? Or AI, how to define it?
Really run out to here. Sorry. So the question was, when we have a AM model we want to use, how do we pick the layers and nodes? We really run kind of a parametric study. So you can actually go from like 1 layer to 5 layer with 5 nodes to 10 nodes, and then just run a global study on not a whole training data set, but a few data sets. And then there are a bunch of algorithms can do that for you, and then we'll give back like which one is the best for your case.
So they actually gave some.
Yeah.
Okay.
So it's so if you never really played with AI, I just want to say it's pretty well developed. You can almost have a UI interface where you just say, this is my data, this is my output. Please train a machine learning model for me. And there are softwares, Python packages can do this for you. You don't need to really spend any time. Of course, you need to check whether this really give you the proper prediction after you get the model. Yeah.
Good.
Thank you.
I have a question. So you mentioned that when not getting the result that you expected, you can increase your ANN complexity. So do you do that like by adding more samples or adding more categories as features, or how do you?
We do both actually.
Okay.
So the first thing is we want to make sure we have enough data points. So we started with only like, I think 200 data points. But then we got like weird behavior on the edge of the compressor envelope, where the performance are harder to predict. I think we then increased the data points first to almost like 4 times higher. We have in the end, I want to say 800 to 1,000 data points just to train a simple model. And the other thing is like we said, I said you can add different AN architectures. Usually you just stay with feed forward or feedback architectures, but you can definitely try this more complicated architectures. And the issue is we don't have enough domain knowledge on ANA ourselves. So we kind of just rely on whatever, other paper. That's how we did this study. We look at other papers and see what they did and use the same method. But it's not something we really can control or understand. That's why I want to dive deeper into more this physics-based, so that we know what we are doing when we train the model.
We have one question in the chat from Frank. It says, what AI models did you use? Cloud-based or local ones that you trained?
We used the local. We just used actually Python package for that. And then there's a software. Man, the name skipped off on my mind, but there's a software right now built for ANN. You can basically just click load the Excel file. Then you tell the software, this is my input, this is my output. Oh. Give me a ANN network for this. And they do a pretty good job. They can also do sensitivity analysis, parametric studies, and they just one button to click. You don't even need to write any code. It's like pretty well developed. Some of the tools in the AI field.
Let's see. He also asked if you have concerns sharing data with cloud-based AI providers for privacy concerns.
Yeah, we do. Everyone do. So we don't really share our data with like cloud-based AI. Like I use ChatGPT, but I never really give ChatGPT the data to, the data I got from testing to do anything. But I may ask ChatGPT to write me a Python code so that I can process my data locally. Yeah. I don't really contribute. And especially if you are work with industrial partners, if you work with some, government agencies, they consider upload things to ChatGPT like a data leakage. So be careful with
that. That's all you guys graduate students. You can retrieve information, but don't contribute. That's usually what I talk.
Yeah.
So I actually have a question to Dr. Fisher also. Like I really agree with you on critical thinking part, especially with engineers.
Yeah.
But the information is so easy to get. Even the homework question answers you can directly get from ChatGPT, right? So nowadays, for professors, what can we do to encourage students take the hard path rather than the easy, convenient path, but they lost the critical thinking ability?
Yes.
So what can we do?
I'm
so confused.
That's a real challenge. With all the fundamental textbook-based courses, heat transfer, thermodynamics, you don't even have to type the problem in. You can take a picture of the graph. You guys all know this. Yeah, you can put. So what I believe that we need to do is and Dr. Liu started doing this in his heat transfer class, caused all kinds of consternation among the students, is just switching from the closed form problem check, like can you do this closed form problem, to much more sort of critical thinking analysis type of if you change this temperature, if it goes up, what happens to this output? And that makes them think in terms of the system. It makes them apply. In my thermal fluids design class, they still, I've taken them back actually to the old psychrometric charts and the pH diagrams, and I make them do the critical thinking and show it on the pH diagrams and on the psychrometric charts. And that still is, I can tell by how closely they pay attention when I explain this. That still is not available. I give if I give a homework assignment and I put a textbook problem in there, they're all done, right? All done. And they don't know how to do the problem, of course, but I think, yeah, to do the manual work, I think where you want them to do calculations, make them do it on a psychrometric chart, and then to go and ask the more they have the more open questions that require them to think about trends and processes and not so much about a computational method.
But there's something they have to do, like fundamental, right? Like if you teach elementary school students, they just have to practice.
They have to practice.
Yeah, but there's certain things just they can easily find from ChatGPT.
Yes,
that's the problem.
Yes, we have not. I mean, it's a big problem, really big problem, because I think you do. I think we have a whole generation of engineering students coming out who can do this.
Well, yeah, mine is just to weigh into the conversation, because I also had that in mind. I feel like something that could also help is creating awareness, like an awareness creation where students can be educated about AI. I mean, like this seminar opened my eyes a lot to like many things that happens underground, how the AI works. And I think if that awareness is, passed across to students, they would begin to appreciate what they do in the classroom.
Mm-hmm.
They will begin to appreciate hard work more, and they will begin to like set boundaries as they use the AI. So maybe that's something that influencers like directors of schools could bring to like, the faculty in different colleges, and then push that out, and that may help.
Yeah. Very good.
I think something what you said kind of brings me, reminds me of, we had a heating and we had a HVAC course, like refrigeration and air conditioning was the course name. And there was a 20-mark question, and there was a psychrometric chart provided. And the question was nothing about solving the pH diagram or anything. It was just basic heat transfer. It said if you have a refrigerator, and it gave the boundary conditions and it gave the conditions for conduction and convection, basically you had to find what was the tonnage of refrigeration that you would require to cool this chamber. And nothing from what you just basically had to calculate what was the heat loss from the system and basically convert that into tonnage of refrigeration. And I see my peers going like flapping through the psychrometric chart, go, where's the data for this to like apply? And I'm like, that's such a good way to like, the whole semester we read how to use psychrometric charts. The exam, nothing to do with it. So that was like, I think it just goes back to like, okay, if you know the concept and if you can apply it, it doesn't matter.
Mm-hmm.
Like, if it's a textbook problem or anything like that. And I think as educators, if we get into academia, we have to be like, okay, we have to trick them into thinking critically rather than like give them the questions that are already out there.
I'll just give you one example very quickly. In one of the exam I did recently, it's a heat transfer course, and you need to calculate like a fin efficiency if you have a fin, right, tube and fin. I just asked what's a fin efficiency, like tell me in plain human language what's a fin efficiency, and many students get the calculation correct, but they don't know what's a fin efficiency.
Right.
So only like 20% get that. What's the definition of fin efficiency correct? But then probably 60% gets the calculation correct. I was like, you are engineer, you are calculating something, you don't know what it is, but what's the meaning of that, right?
Yeah.
So
There, I see so many of those situations.
Yeah.
Well, I think given the time we have,
yeah.
we can call it off. I mean, this is a very good discussion.
We like the discussion.
Longer than I should.
No, it's fine.
It's
Actually, a lot of times when we have seminars, it's mostly deep dive into AI and machine learning stuff. This is more like, okay.
Everyone on
as you
Zoom,
said,
thank you
we're
very
not
much
doing
for
AI,
attending.
you can also
I'm
apply
gonna
it across-
shut off the recording now. And if you want to continue this conversation, you can reach out to me and I can share their contact info, or come to our GSC seminars or GSC meetings.
I mean, I guess in the sense, like, probably you have the luxury of doing all the